Now we're in section 2.3 differentiation formulas. And the idea is we've spent some time using the limit definition of a derivative, which is great, but a lot of work. And so luckily there are easier ways to take derivatives because of the fact that the limit definition is true. So one thing to remember is that when you take a derivative, you are getting the slope of the function at any point. So when we look at some of the basic properties here, we have that if f of x, is c, c being a constant, then the derivative of a constant, you want to remember that if a function is a constant, it's just a horizontal line, and the slope of a horizontal line is just 0. So that tells us that the derivative of any constant is 0. Now, if f of x equals x, and we've seen this on like the one side of the absolute value problem, the right side, again, it's just the slope of that line. And I mean, so of course, f of x equals x just looks like this. And that line has a constant slope. The slope doesn't change. The derivative is just 1. And of course, this is just using some other notation just so you can see it. And that derivative is also 1. So here is some examples of functions and their derivatives. So if you want, you can take a moment and you can try to guess what the pattern is for those functions since you know what their derivatives. So take a look at, these are basic power functions. They've got x to a power. So see if you can take a guess on what that is. Once you've done that, unpause it and head to the next part. So this leads us to the power rule. And maybe I'll come back over here really quick. So what we're seeing here is, it's a little bit easier on the second and the third one. What we are seeing here is the exponent is coming down to the front. And then you're also noticing that the exponent is losing 1 from its power. So that is happening. Dun, 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 dun. And it's even happening here. So notice that this does have a power of 1. So this is heading to the front, and this is subtracting 1. We just don't need to write the 1 at the bottom there. So it leads us to the power rule. And the power rule says, if you have a function that is x to a power, and that is a positive integer, so we want to be a little bit careful, positive integer, so a whole number that is positive, then the derivative is going to be bringing that exponent down, multiplying by x to the, and then losing 1 from the exponent, n minus 1. So that's the power rule for any function x to the n. And the proof of it is this. So we have our general limit definition of the derivative. What you're seeing here is it's already been set up for x to the n. So notice that we have put in x plus h to the n and minus x to the n over h. So it's just putting in that function x to the n. And now we're going to see what happens. So when we think about multiplying this out, we still are trying to get rid of the h. That's the whole idea here in that denominator. So I'm going to do this kind of long version here. Okay, so this is something that you have to kind of know a little bit about maybe from pre-calculus, but x plus h to the n is similar to saying, say, x plus 5, say, to the 6th, something like that, for example. This is a binomial raised to a power. And so this is coming from the binomial theorem. And so there's a whole thing that goes along here that you can look up the binomial theorem, but there's a pattern. So the first term, when you take x plus h and raise it to the n, you're going to have x to the n. That's going to always be the first term, no matter what n is. And then your middle terms, the first one is going to be n times x times n minus 1. And then the next term, times h, times h there. And then the next term is going to be, so n is the coefficient for the second term. The next coefficient is n times n minus 1 over 2. So it's all based on what your exponent is. That's what's coming. This is always true though, but we just have to use these general. And then x to the n minus 2 times h squared. So what you want to see with the binomial theorem is what happens is you start with x to the n. Every term, the n goes down by 1. And every time, the h is going to go up by 1. So notice the first term just is x to the n. That has h to the 0. And then you have h to the power of 1 in the second term, h squared in the third term, as you can see. And then we just keep going. So there's a bunch of terms in between depending on what your n is. They don't matter to us, so don't worry. And then what we have is the last term, which is plus h to the n. So all the terms in the middle are x going down by 1, h going up by 1, until there's no more x to the 0, and you have h to the n. So that's the binomial theorem. Again, you're welcome to look that up to remind yourself if you have or haven't seen it. And then, of course, don't forget that we have to subtract h to the n, x to the n, minus x to the n. And then that's still all over h. So what you should see now, we're not quite there yet, is, of course, that we have, I'll put it in a different color, that we have an x to the n that simplifies with this x to the n over here. That's key. Because what you should then see is, even though we have all this crazy stuff in between, you know, just a lot of stuff there, that each term has an h. So we have n times x to the n minus 1 times h, plus here's the second term, n times n minus 1 over 2. That's the coefficient of the second term, x to the n minus 2. It's like, how, at what point do I decide? Just gonna erase a little bit. Okay, x to the n minus 2 times h squared, and then all our terms in between, and then h to the n, all over h. So that's what we're left with. Again, everything that we have has h. So what we want to notice now is that this h here is going to simplify with all the h's in the numerator, meaning one of all the h's. So this h here is going to simplify with this h here. It's going to simplify with this h here, so that is just to the power of 1. And it's going to simplify with all the h's to reduce them by 1 in between. And it's going to simplify this h here to be n minus 1. So it's going to take out one of those h's by simplifying. And this is also just a plus here. So what we're left with, we're almost there. What we're left with, limit as h goes to 0. We have n times x to the n minus 1. That's all we have in the first term. Then the second term is plus that n times n minus 1 over 2 times x to the n minus 2 times just h, plus, and then we have the terms in between, and we have h to the n minus 1. So the reason why this is important, and just going to make this a little bit more on the level, I guess we would say, is because now we can take our limit. Now we no longer are dealing with a division by h. So every term but the first one has an h in it. So when we take the limit, this whole thing's going to go to 0. Every term in between goes to 0, and this term goes to 0 because they all have h. So what that tells us is that all we have left is just n times x to the n minus 1. It had no h in it, so there was no limit to deal with. But it, of course, gives us that limit and that derivative. So now we have that. So this is equal to f prime of x for f of x equaling x to the n. So now we have proven it. So that's a big deal. We have proved it. So now we can use it, which is great. Now I did it there with the idea of a positive integer exponent, but just know that if n is any real number, it is still true. So you could have decimals, fractions, rational numbers as your exponents. It's still true. It's just a lot harder to prove that way. So we're going to say that it is true because it is. You have to take that as fact. We won't prove it here, but it does allow us again to use it. So there's a few other rules as well. Stuff that's not particularly surprising. C is a constant, F is differentiable. Then the idea here is when you look at this, it's telling you take the derivative d dx of this c times f of x. So like we can often do with constants, you can bring that out and then take the derivative of your function and then multiply it back by your constant. So you can pull your constant out, and sometimes that can be a little bit easier. So there's some examples here. Find the derivatives of each of the following functions. So you are totally welcome to pause, see if you can find the derivatives using this power rule, and then come back and see if you got them right. So for the first one, it is very basic power rule. We're going to bring down that 7. We're going to have x. We're going to subtract 1 from the numerator. You do not have to write that every step. This is a more basic derivative, so you're welcome to just go right to the answer. That is okay. For b, you might be thinking, I see a square root. Yes, you do. But you want to remind yourself that all those roots can be rewritten with an exponent. So in this case, you'll have x to the 1/2, and then it just follows the same pattern. We're going to bring down the 1/2, we're going to have x, and then we're going to subtract 1 from the 1/2, and that's going to give us a -1/2. That is fine, or you can rewrite that with the square root of x in a denominator. So either one of those is true and valid. And then the last one here, the idea is from that number 4 at the top. If you take the 5, you can then take the derivative of x to the 8th, which is 8 times x to the 7th, and then multiply it 40x to the 7th. Over time, typically students would just go right from f of x being 5x to the 8th to immediately saying 40x to the 7th without doing this intermediate step. And again, because it's just one term, that's okay as you go. So another very handy and popular thing is the fact that if you have two functions f and g and they are both differentiable, then you can take their derivative by simply taking the derivative of each piece. So you can take the derivative of f of x, and then you can add or subtract the derivative of g of x. So not too surprising there, but the point is you can separate them and take each derivative separately. And this allows us to do a lot of stuff, one of which is the problem at the top of the next page, which is some function v of x. Just to be exciting, you're asked to find the derivative. What you want to see is you're taking the derivative of 1, 2, 3, 4 pieces. And all of them are using what we've been talking about so far today. So if you want, again, you're welcome to pause this, do this problem, come back, see if you are right. So the derivative here, we're going to bring down that 3. I'm just going to go ahead and multiply it by the 6 to get 18x squared. For the second term, again, I can bring down the 2. That gets multiplied by the 4 to get 8. Subtracting 1 from 2 is just 1, so I get 8x. Remember that the derivative of x, I can just pull out kind of that minus sign because it's just a negative. Take the derivative of x, which is 1. And then we don't want to forget that the derivative of a constant, 7, is just 0. So we're done. That's the whole thing. Nothing else. For the second example here, find an equation of the tangent line to a curve. Now our job is to find that tangent line. And so we don't want to forget that we need 2 things to find the equation of a line. And one of them, of course, is a point. And then, of course, we have the slope. So the point is we have x equals 1. And so when x equals 1, what we can do is just plug that into our curve, which would be 1 squared minus 2 over 1. So I'm just putting that in for y, I'm putting in 1 in for x to find y. And I get 1 minus 2, or -1. So we have our point 1, -1. Ta-da. But then we still need our slope. So before we can actually find the equation of a line, we need our slope. So maybe I'll head down here and I'll put slope. And so what we have learned is that what we need to do is find the derivative. So I'm going to write y equals x squared. One thing that you can do that is helpful is rewriting things when you have variables in the denominator. So don't forget that this is the same as saying 2 times x to the -1. So we can bring that up and write that with a negative exponent. And then that allows us to use the power rule. We cannot use the power rule unless we have something of the form x to the n. So it does need to be rewritten. You would not be able to take the derivative the way that you're seeing it. So we want to rewrite it. And then now I can take the derivative using the power rule. I'm going to have 2x I'm going to then use the power rule on this second piece. I'm going to have -1 times -2. And then I'm going to subtract 1 from a -1. And that's actually going to give me a -2. So we want to pay attention to that. So you can also say y prime equals 2x plus 2 over x squared. So the 2 is positive. It has no negative exponent on it. So that's going to be in the numerator. So we are almost there. The only thing we need to do, of course, is find out, well, what is the slope at 1? What we found was the slope at any point on that curve. Now we need the slope at 1. So we're going to plug it in. We'll have 2 times 1 plus 2 over 1 squared. So you can evaluate that. So no surprises here. We get a slope of 4. So we have our point, we have our slope, and now, as always, we just go to point slope form. If you want to bust out slope intercept form and then find your b and do it that way, that is okay. I'm going to have y minus -1 equals 4x minus 1. So you're welcome to then write this in slope intercept form if you want to pause and do that. So typically, if you're asked to write the equation of a line, writing it in slope-intercept form is how we want to see it. It tells us the slope, tells us the y-intercept, kind of gives us some important stuff. And so our answer here, the equation of the tangent line to that curve is 4x minus 5. So if you have the curve x squared minus 2 over x, it looks like something. But at 1, if you draw the tangent line, that's going to be the equation of that tangent line.